You're watching the Learning Channel.
The planet Mars. Not the Mars of today, but a future Mars. A world of seas, continents, and vegetation. A place to live. To remake the red planet in Earth's image will require engineering of the boldest order. For clouds to sail in breathable air, that's the challenge. To transform a frigid global desert into a place where water flows and plants begin to grow. But more than that, to establish life on Mars would end uncertainty. For the first time, we'd no longer ask, are we alone in space? Right now, this is the only place we know life to be. Yet, when the spacecraft Galileo swung past Earth, it detected just one hint of life. Lots of oxygen. Galileo saw a moon and a planet, no animals or plants. With different sensors, of course, Galileo would have seen cities. The nightlights of America's west coast. And Florida. Surely the lights of life. From Earth, we wonder at lights of a different kind. The stars and galaxies of the cosmos. Our own galaxy, the Milky Way, is home to billions of stars, millions of them ordinary stars like our sun. Nobody knows, but it's fair to assume that many of those stars have planets, and where there are planets, there's potential for life. If that life is intelligent, we should be hearing from it. That's the reasoning of radio astronomers. With great dishes, they listen for signals from beyond. Depressingly, after years and years, there's been not a peep. Yet radio telescopes provide the only hope that something will be heard. And they tell astronomers that the chemistry of life is out there. It floats in clouds of gas and dust throughout our galaxy, complex organic molecules, like the molecules that gave rise to life on Earth. Earth is a small planet of an insignificant star in the suburbs of our galaxy. As we look inward at the 200 billion stars of the Milky Way, surely there's life out there. It's in the nature of our species to journey outward, to explore. Continent by continent, we colonized the world. Now we're contemplating space stations, bridges to the planets. Sooner or later, we'll reach them. And maybe we'll develop technology to carry us onward, across light years of space to the stars. For the present, We search for life with simpler means, the instruments of astronomy. Already, an observation from Earth orbit has sparked excitement. Scientists were looking for stars so young that disks of material still surrounded them, halos from which planets might form. Here, in a great cloud of gas and dust, 1,300 light-years from Earth, the Hubble Space Telescope made a remarkable discovery. It was searching in the Orion Nebula. There it is, Hubble's picture of a star surrounded by a black cocoon of dust. Was this how our solar system developed? In time, will this star shine bright and clear when planets are formed from the disk? Billions of years from now, will one of those planets develop life? Will intelligent beings stare out into space? Will they too wonder, are we alone?
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
Even for a star with planets, there's no guarantee of life. Take our solar system. Nearest the Sun, Mercury, scorched and barren, impossible for life. And at the other extreme, farthest from the Sun, it's too cold and dark for life. Pluto is out. So are the gas giants like Neptune and Uranus. The same for Saturn. There are more likely planets, like Venus, virtually the twin of Earth, and Mars, our smaller neighbor. But as we know, life developed only on Earth. The question is, why? Let's go back to the origin of the solar system. 4.5 billion years ago, as the sun began to shine, the planets were born out of the disk that swirled about it. The infant Earth was a compact little world, like Venus and Mars, formed from the heavier elements of the disk. But it was a place we'd never recognize. Other than a thin crust, Earth was a molten ball. It seethed with heat and energy, volcanoes everywhere. The first atmosphere was poisonous gases. As they rose, they cooled, clouds formed, it rained, and then there were seas. It rained and rained for millions of years. Eventually, oceans covered 4/5 of the planet. Earth was a world transformed, but still without life. Rain did the trick. Over eons, organic molecules were flushed from the atmosphere. The oceans became a broth of organic matter. Then, about 3.5 billion years ago, probably in warm, shallow waters, molecules began to replicate. They started to take in nutrients, even to use sunlight as food. Life on Earth had begun. As the volcanoes quieted down, the atmosphere cleared and changed. More and more oxygen was pumped out by green plants as they evolved. When the first animals crawled from the sea, there was good air to breathe. Our benign and beautiful planet had evolved. Increasingly, scientists believe life on Earth may have been triggered by organic molecules carried here on comets. Perhaps, but then why not on Venus? Just as many comets have fallen there as on Earth, Yet Venus is devoid of life. And why not on Mars? Next to Earth, Mars is the most likely incubator of life. We know it once had water. There are polar ice caps to prove it. And volcanic peaks point to an exciting past. This one, Olympus Mons, is over 15 miles high, the tallest mountain in the solar system. The Martian volcanoes have long been quiet, but once they fueled an atmosphere like that of the early Earth. If Mars had a similar geological past, why not a parallel biology? We're skimming along Mariner Valley, a rift that would stretch from New York to California. If Mars had oceans, this would be a great waterway. The ice caps of Mars shrink and grow with the seasons. Some of the ice is frozen carbon dioxide, but there's water ice too. It supports a theory that water once flowed on Mars. But if it did, what went wrong? There's more evidence of a watery past in photographs from space probes. Here, a network of channels. And a teardrop, molded surely by flowing water. Almost certainly we will land on Mars. In time, we will build permanent stations on Mars. After all, the trip from Earth will take a year. We will need airtight shelters. The wispy atmosphere of carbon dioxide is unbreathable. Explorers will wear pressurized suits and drive Martian rovers. They'll search for water. Reservoirs of ice are thought to lie beneath the surface. And they'll take samples for evidence of life. Fossils, perhaps, or microbes still surviving in the dirt. The big plan will come even later, the dream of turning Mars into a second Earth.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
To transform Mars, generators would be built to release vast quantities of carbon dioxide. As the atmosphere thickened and warmed, water would appear. Released from permafrost and the polar caps, it would form seas. The greening of Mars would be underway. Everywhere, specially sown plants would pump out oxygen. Imperceptibly, there'd be an atmosphere to breathe. Mars in the image of Earth. The process would take thousands of years, and it's still science fiction. But on a terraformed Mars, imagine a cruise along Mariner Valley. In its waters, our descendants could gaze at reflections of Martians, reflections of themselves. Venus, Earth's other neighbor. Did life ever develop here? In size and density, it's the twin of Earth. Forever shrouded by cloud, Venus, until recently, concealed its nature. Now, thanks to space probes with radar, we've glimpsed the surface. The awful truth is revealed. Venus suffers the ultimate runaway greenhouse effect. With an atmosphere 96% carbon dioxide, the sun's heat is trapped. Venus is an inferno. To this day, these are the only pictures of the surface. They were radioed to Earth before the landing craft melted. The rock was basalt, probably slabs of lava. Radar mappers painted a better picture. They electronically pierced the clouds to give the first wide-angle images of Venus, and volcanoes were revealed. But this was a flatter planet than expected. There are fewer craters and less contour than on Earth or Mars. The surface is like an ocean bed, smoothed by currents. Radar had more delights. Stripped of its cloudy veil, we could now fly low over the surface of Venus. This is the topography of Venus, a computer enhancement of radar data. Heights are exaggerated and color guessed at, but otherwise the features are accurate. Craters, evidence of missiles from space. These pancakes are volcanic eruptions crushed by the atmosphere. Pressure here is 90 times greater than on Earth. A mile-high volcano, probably extinct. Of all the planets, Venus has the most volcanoes. It's also hell. Temperature, 900 degrees. Visibility distorted, winds and lightning storms, and when it rains, it may pour sulfuric acid. A probe descends into another cloudy world, the gassy colossus of Jupiter. The search for other life continues. After the sterility of Venus and Mars, this is the next place to look. Although Jupiter is nearly 500 million miles from the Sun, it's not a frigid ball of gas. As this infrared image shows, there are bands of heat radiation. Jupiter emits more energy than it receives. But the tops of its clouds are cold, more than 200 degrees below zero, and they're laced with poisons like ammonia and methane. It's a hostile place. Yet lower down, temperatures rise. Complex organic molecules are known to be present. Some scientists suggest that the chemistry and energy here resemble the conditions on Earth when life took hold. Might this be a birthplace like Earth? Do organisms float in this Jovian soup? Another possible incubator of life, the great moon Europa, one of 16 that orbit Jupiter. Beneath a thin, icy crust may flow a global ocean where perhaps volcanoes erupt. As in our own oceans, creatures may cling to volcanic vents, feeding on chemicals, thriving in darkness. Even farther from the sun, we'll also probe this bland facade. Enveloped in smog and mystery, it's Titan, a planet-sized moon of Saturn. Beneath the haze, scientists believe that Titan has the chemical prerequisites of life: hydrocarbon snow and methane lakes. It's like the Earth in deep freeze. But one day, they say, Titan may come alive. 5 billion years from now, Titan will thaw. The sun will begin to die and become a red giant, boiling away the oceans of Earth. But here, for a time, life may spark and flourish. And who knows, Titan could become a lifeboat for the human race. By then, Earth will be a cinder.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
In the short term, this search for life has been in vain. Maybe, just maybe, the simplest organisms lurk on the moon Europa or the planet Mars. But beyond the solar system, in the family of stars we call our galaxy, we've detected no inkling of intelligent life. Night and day, we scan the skies for a kindred call, a message that would tell us we are not alone. Hundreds, perhaps thousands of years from now, we may encounter the beings of other worlds. Meanwhile, only we can populate the planets and journey to the stars. It's as close as Dallas is to Houston, orbiting just 240 miles from Earth, the Russian spacecraft Mir. Just a camera shot beneath, the familiarity of home. There's Mount Fuji. All that shields these men from the lethal radiation of space is their tiny craft. Our atmosphere does the same for Earth. So does the magnetic field that cocoons our planet. Dangerous particles blowing from the sun are deflected. Sometimes they reach the upper atmosphere. They flicker as the lights of the aurora. But largely this radiation goes unseen. Even the most powerful optical telescope detects only a fraction of what is there. For the big picture, astronomers must sense all radiations. Somehow, some way, they must conjure up the invisible cosmos. Science has revealed a universe more complex than ever imagined. This is its structure, strands of matter strewn through unimaginable emptiness. Like dewdrops on a spider's web, each point of light is a cluster of thousands of galaxies. Each galaxy contains billions of stars. Our galaxy, the Milky Way, belongs to a local cluster. Like clusters everywhere, the galaxies are drawn to one another by gravity. A computer shows how they swirl and collide. In the process, they release energy. Astronomers detect it as electromagnetic radiation. Exploding stars add to that radiation. So too do regions where stars are born and where stars disappear into black holes. Radiation tells us of quasars, those enigmatic objects at the limits of our understanding and our vision. Imagine the universe as an orchestra. Then imagine hearing only one note, middle C. That's what it's like when we look at the sky. We get one note instead of the full cosmic orchestra. The human eye detects just a part of the electromagnetic spectrum. The spectrum stretches from gamma rays at one end to radio waves at the other. In the middle is visible light, the colors of the rainbow, the few wavelengths evident to our eyes. The night sky appears brilliant and serene. We're blind to its turmoil. Only now, with a new astronomy, do we sense the whole picture. To see that picture, that radiation, we need sensors right across the spectrum. But because most radiation is absorbed by the atmosphere, we have detectors in space. In Earth orbit, this is a gamma-ray observatory. Here's an image from an X-ray craft. Impossible to see optically. It's a pocket of gas trapped among galaxies. In mid-spectrum, the Hubble Space Telescope works in ultraviolet and near-infrared as well as visible light. Wavelengths are gathered by COBE, the Cosmic Background Explorer, a COBE picture of our galaxy, again invisible optically. For radiation that penetrates the atmosphere, gigantic dishes listen for whispers from space on radio. And to complete the picture, visible light is still collected by the first instruments of astronomy. With this primitive antenna, radio noise from space was first picked up by the American Carl Jansky. It was 1931. The noise was from our galaxy. Today, radio telescopes probe the heart of the galaxy and the depths of the universe. Around the clock, observers track the skies. Radio sees day and night, and whatever the weather. This receiver in Effelsberg, Germany, is the biggest steerable dish in the world. It's more than 300 feet across. Radio waves are bounced from the dish to a focal point in the horn above its center. Computers do the rest, turning radio into pictures. Pictures like this of the center of the Milky Way. Here's the same region seen optically. Pretty enough, but compared with the penetration of radio, like looking through steam on a window. If we could see in radio, this would be the sky. The dots are no mere stars, but galaxies and groups of galaxies. Radio telescopes map the cosmos. They've discovered quasars and their elderly relatives, radio galaxies. They trace neutron stars, the relics of supernovas, and clouds of hot gas that emit no visible light. Teams of dishes work in unison. By linking them electronically, astronomers create a giant receiver. Each dish sees from a slightly different perspective. Together, they synthesize a sharper image. This picture is such a composite. It shows red billows of gas surrounding a galaxy. An ordinary telescope would see just the galaxy.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
Centaurus A, a galaxy in turmoil, a photograph through a powerful optical telescope. Map Centaurus A with a radio telescope and we see the turmoil. Two huge lobes of radiation stretch out from the galactic center. They emit intense radio signals. Here, another double radio source, the unusual galaxy Cygnus A. The optical image completely misses the action. And here, a galaxy traveling at speed through the intergalactic medium. High-energy particles in jets. By modeling their behavior on a supercomputer, astronomers are learning about a giant galaxy in the constellation of Virgo. It's Virgo A, one of the most powerful radio sources in the sky. Radio reveals a jet of escaping radiation. Imaged over 10 years at the VLA in New Mexico, the jet is a sign of feverish activity at the heart of the galaxy. By analyzing the jet section by section, observers time-lapsed its phenomenal development. The galaxy is ejecting material at an incredible rate, apparently faster than the speed of light. But that's impossible, an illusion caused by the angle at which we observe the jet. Radio images have been augmented by the Hubble Space Telescope. Here, Hubble's optical close-up of the jet. Computer animation shows what's happening. The jet blasts from the core of the galaxy. It's one of two, produced as a spiraling disk of matter, is sucked into a massive black hole. Similar jets shoot from black holes in quasars, the most intense concentrations of energy anywhere. Is there a black hole at the heart of our own galaxy? No one really knows, but this radio image of our galactic center suggests it's possible. The S-shape on the right is the clue. Closer in, the S hints at material swirling around an invisible core. Closer still, but there's no sign of radiation jets. Scientists are puzzled. Perhaps our black hole is between meals, waiting for the next stellar dish to wander by.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
The Hubble Space Telescope has triple vision. It works in the visible range, plus ultraviolet and infrared. In the visible band, this is the smoggy face of Titan, the largest moon of Saturn. But here in infrared, Hubble cuts through the clouds to reveal what may be continents and oceans. Infrared radiation can be detected from Earth. One of the best places is atop Mauna Kea, an extinct volcano in Hawaii. High above the clouds, the air is clear and dry, excellent for observation. But there's an even better place to catch infrared. The South Pole. Believe it or not, it's drier here than on Mauna Kea. This detector at the Scott Amundsen base is the clearest earthly eye in infrared. Infrared astronomy has come of age during the last decade. Its wavelengths are so close to visible light that the images seem optical. Nonetheless, they reveal aspects of the Milky Way that once went undetected. One of the most celebrated vistas of our galaxy, the Orion Nebula, but in the visible band, most of its stars are obscured. Infrared lifts the dusty curtain. There they are, scores of stars, bright and young. Optical astronomers aren't sure what's happening in the heart of the nebula. Infrared reveals a catastrophe. A young star has blown itself to pieces just as it was starting to shine. Still in Orion, and enveloped by dust in the bowl of the nebula, lurk the trapezium stars. In infrared, the dust settles and the stars shine through. In an optical telescope, an astronomer's disk blocks the light of a star. It reveals a halo. Using this method, infrared detects a disk of dust surrounding Beta Pictoris, one of the nearest stars to Earth.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
Earth's atmosphere absorbs extreme ultraviolet, so we use spacecraft to catch it. This satellite, the Extreme Ultraviolet Explorer, probes our galactic neighborhood. The Explorer has discovered we live in a bubble, a gigantic envelope of clear space. The bubble is formed of cool, thin gas extending several hundred light years around the solar system. But why? What blew the bubble? The explorer has found some clues. Methodically, it scanned the cosmos segment by segment, the task to log every source of ultraviolet radiation. While assembling these swaths of space, the explorer made the most exciting observations close to home. Near the stars of the Pleiades, the Seven Sisters, it discovered this black patch, a bubble of gas. Indeed, it found several bubbles in our vicinity. One theory says that they're holes blasted by the death of gigantic stars, the explosion of supernovas. Along the spectrum, in the short waves of gamma radiation, the dot at the center is Geminga, the remains of a huge star that exploded 300,000 years ago and blew the bubble that surrounds the solar system. All that's left of Geminga is a neutron star with an intense magnetic field. Geminga's explosion was a regular supernova, but if a supergiant explodes, the result can be a black hole. Everything, including the neutron star, falls in on itself. Nothing remains. Sensing such sources of radiation is the job of the Compton Gamma Ray Observatory. It's logged hundreds of black holes and neutron stars, but it's also picking up shorter random bursts of gamma radiation. They come from every direction, and no one knows what they are. They're far outnumbered by long-term signals from the likes of black holes. One possibility is that short bursts occur when neutron stars collide. Compton is building an exotic map of the gamma ray sources all around us. La Palma in the Canary Islands. Here, at almost 8,000 feet, these aren't beehives, but detectors looking for the effects of cosmic radiation hitting Earth's atmosphere. And this fly's eye is picking up flashes of light from high-energy gamma rays. These emissions reach us from the farthest corners of the galaxy and beyond. And they're a mystery. We don't know how they began their journey or when. One day, perhaps La Palma will help solve the riddle. COBE, the Cosmic Background Explorer, was launched to look back at the beginning of the universe. Through clouds of dust and gas, it set out to find the coolest radiation in the cosmos, radiation that's been around since before the galaxies. It charted a remarkable map of the early universe. Here it is, 500,000 years after the Big Bang. From more than 10 billion years ago, COBE's data seems to confirm how things began. Light and energy became matter. Under the influence of gravity, subatomic particles clumped together. From radiation and dust, galaxies of stars evolved. One was the Milky Way. Within it, 5 billion years ago, our sun and the planets were born. Today, we peer back through the instruments of new astronomy, and we're still asking the old questions. Those answers must come from the invisible cosmos. The Milky Way. So ghostly, it's invisible in moonlight. Only after the moon has set does the Milky Way appear. Only in the darkest and clearest skies do we glimpse its galactic splendors. This is the Milky Way. In ancient Greece, Aristotle thought it was a band of fire fueled by the vapors of Earth. Democritus said it was a great collection of stars, so distant they merged with one another. Democritus was right. The Milky Way is a galaxy, an island universe, a family of 200 billion stars. We belong to that family. Our sun is one of these stars, a single point of light in a swarm of energy and brilliance. But because we're part of the galaxy, we don't see it as a whole. For an overall impression, we must seek a look-alike among the billions of galaxies that populate the universe. Astronomers call this NGC 891, a galaxy over 40 million light-years away. It's a dead ringer for the Milky Way. In this perspective, we're looking sideways at its vast disk of stars. This satellite picture of the Milky Way could be its twin. It's our partial view of our galaxy. If we could escape from the plane of our galactic disk, we could see the Milky Way in all its splendor. The ingredients of the Milky Way are stars and restless clouds of dust and gas. They're molded by gigantic forces, the push and pull of gravity, magnetism, and nuclear fusion. These are the true colors of our galaxy, nature in the raw. With radio telescopes, astronomers penetrate the clouds of cosmic debris that obscure so much of the Milky Way. Toward the galactic center, in the false colors of radio waves, they spotted vast clouds of hydrogen gas. Such information, along with infrared images like this, help scientists map the galaxy. And by looking at other galaxies, they're learning about structure. Some 25 million light-years away, this is M83. Like the Milky Way, a spiral. On a computer, we see the stars of the Milky Way orbiting the galactic center. Clusters of ancient stars hover outside the disk like bees around a flower. In a blue arm of the galaxy, 2/3 of the way from the center, is our star, the Sun. Here in these galactic suburbs, stars begin their lives. This bubble of hydrogen in a neighboring arm is such a birthplace. Within the bubble, matter is squeezing ever denser. Gravity increases, temperatures soar, nuclear fusion begins, and stars are born. A photograph of that stellar nursery. The oldest stars are those groups hovering outside the central disk. They're called globular clusters, each comprising up to 1 million stars. The most elderly clusters are 12 billion years old, nearly 3 times the age of the Sun. One of them is a monster, almost a galaxy itself, a retirement home to 6 million stars. In the orange glow are more ancient stars, billions of them. They form a great bulge at the heart of the Milky Way. Farther out, younger stars appear blue. From Earth, we're looking along the plane of the galactic disk toward the bulge of orange stars at the center. On Earth, the best views are in winter from the southern hemisphere. This remarkable time-lapse tracks the Milky Way over one night. Like the course of the Sun during the day, it's not the Milky Way that's moving, it's our planet turning on its axis. From the top of the picture, the bright center of the galaxy moves into the frame. A wispy galactic arm extends to the right. The Milky Way is so big that for light to travel from one side to the other takes 100,000 years.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
For 20 years, this man has had the sharpest focus on our galaxy. David Malan, photographic scientist at the Anglo-Australian Observatory in New South Wales. Malan's lenses are gigantic telescopes. This is his wide angle. It's the UK Schmidt telescope, with an aperture nearly 4 feet wide, focused on the galaxy. The Schmidt has no eyepiece. It's designed for electronic and photographic observation. Instead of film, the camera is loaded with a plate of specially sensitized glass, 14 inches square. An instrument nearby does the close-ups. With a mirror almost 13 feet wide, this is one of the biggest telescopes in the southern hemisphere, the 3.9-meter Anglo-Australian, perched above the outback. Through clear, unpolluted skies, Malin pursues his craft, basic photography penetrating the depths of the galaxy. The telescope is so big, Malin can ride in its mechanism.
Right, see you in 3 hours. Okay, Kevin, next object, please.
Okay, Dave, here we go.
In the prime focus cage, like an astronaut in a module, Malin takes off for a night in the stars. One picture takes hours. It's a composite, 3 successive exposures in green, red, and blue. As Malin loads the first plate, his vigil begins. Tonight's exposure is short, only 3 hours. But if the object is faint, it could take 3 exposures over 3 nights, each lasting 8 hours. Malin works with his back to the stars. Their light is collected in a huge mirror beneath his cage. It reflects to a focal point in the cage and in the camera. The telescope tracks the target by compensating exactly for the spin of the Earth. Back in the darkroom, Malin matches the 3 exposures. Only by returning to basic technique can he squeeze the maximum detail from each exposure. The ingenious composition he's building produces an image packed with information. It's as though we were viewing the galaxy with eyes 100 times more sensitive to color and light. The naked eye sees the galaxy in black and white. Malin's composites unveil natural color. But they're not just pretty pictures. They're a key to discovery. They reveal the nature and relationship of stars, the evolution of the Milky Way.
There's a structure, a crosshair structure inside the telescope, and light scatters around that.
Malin is astronomy's most celebrated photographer.
Thanks for coming.
His books and lectures have a double appeal. Amateur astronomers who've looked at the sky in awe and tried to photograph it want to learn to do it better. For professionals, often preoccupied with specifics, he sets their work in context.
This is the kind of coloration you would see. These are not artificial colors. These are the real colors of nature.
David Malin, the man who colors stars. Photographs of the galaxy reveal only part of the story. To peer beyond optical images, astronomers employ a battery of telescopes and spacecraft. They explore in different wavelengths. They detect cold clouds of dust and gas and regions of stellar birth. If any planets orbit nearby stars, these space probes will surely find them. In wavelengths like ultraviolet and infrared, impossible optically, these are views along the plane of the galaxy, looking toward the nucleus of our system. From above, so to speak, this is the view we never get. The great spiral of the Milky Way, a picture map compiled from several wavelengths. Here, in the sector we see from Earth, we begin an odyssey, a journey through David Malin's camera. His photograph of the Eagle Nebula, a cloud of red hydrogen where stars are born, so distant that their light takes 6,000 years to reach us. Another birthplace, the hub of the Trifid Nebula, hydrogen gas and black lanes of dust. In this Malin picture, we pull back from dark peripheral clouds to reveal the brilliance of the Trifid Nebula, whose light they reflect. These stars have blown away their clouds. They're the jewel box, like gems on black cloth. By contrast, there's cloud everywhere. Nebula means cloud. At the same distance, 8,000 light-years, loops of gas are created by stellar winds blowing from the depths of another star-forming region. Back to the picture map, and to a cloud with a tiny pulsing heart. It's the Crab Nebula, the debris of a supernova. Within it spins a pulsar just 10 miles wide. In animation here, the relic of a gigantic star that exploded nearly 1,000 years ago.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
The Rosette Nebula and the Gleam of Youth. At the center, 4,500 light-years away, a nest of bright new stars. But as we focus nearer home, new stars are not to be confused with novas and supernovas. This is a nova in the making. The supergravity of a small, dense star is pulling matter from its companion. In a buildup that happens again and again, there's suddenly a moment of indigestion, and then a bang. To the ancients, it was a new star, a nova. And here, the remnants of a supernova. Again, nothing to do with birth. This is the Cygnus Loop, the entrails of an enormous star that blew itself to pieces 60,000 years ago. But in death, there is renewal. Such gigantic explosions are thought to trigger the formation of other stars, stars like our sun. Supernovas seed the galaxy. Here, hydrogen gas glows red, excited by radiation from hot young stars. Orion heaves with stellar gestation. Below, as a plume of black dust rises in the foreground, another Malin masterpiece, his famous Horsehead Nebula. Science as art. But this is probably the most celebrated object in the heavens. M42, the Great Orion Nebula. Again, by David Malin. From Earth, in the northern hemisphere, our view of the Milky Way. Within it, just discernible, a dark vertical split known as the Aquila Rift. It's not a void, but a band of opaque, sooty dust, 1,600 light-years away. The rift is upper left on the map. Here, we've reached our galactic backyard. At a mere 400 light-years, this is the Coal Sack, not a hole in space, but a black nebula by the Southern Cross. A young star group, the Pleiades, lies at about the same distance. More popularly known as the Seven Sisters, they drift in a thin nebula. Shrouded in a thick nebula, dust of its own making, the great star Antares. It blazes in the constellation of Scorpius. At a distance of 400 light-years, Antares is an aging giant, 300 times wider than the Sun. It's so big that if it explodes as a supernova, Antares could form a black hole. Every nearby star is stripped and consumed. Nature's ultimate trap. Nothing escapes.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
This star is dead. It's the corpse of a giant star that blew out this beautiful shroud, the Helix Nebula. At 700 light-years, the star at the center here is nearly twice as far as the Helix. We're looking at Polaris, a supergiant at the northern pivot of our skies. These are our next-door neighbors, the triplets of Alpha Centauri. The red star, Proxima, is closest of all, at 4.3 light-years from Earth. The twin system known as W Ursa Majoris. Two stars so close, they constantly exchange material. Binaries and multiple stars are surprisingly common. But this is an exception. 3 sets of twins, 6 stars in all, orbiting around one another, 45 light-years away, the waltzing stars of Castor. Most of our neighbors are binaries, like Epsilon Bootis. Finally, on our neighborhood tour, the friendly stars of Ursa Major. Fly through them in space, and they form no pattern. But come back to Earth, and there they are, the Big Dipper, our most familiar stars. Beyond them, our galaxy contains 200 billion other stars, revealed to us now by astrophotography. Dawn seeps into the temple of Abu Simbel. In Egypt, 3,500 years ago, sunrise is a moment of reverence. When the first rays enter the Great Hall, the sun god Ra is reborn. To peoples of old, the sun governed both ritual and routine. The point of sunrise moved each day. The sun was a calendar. The need to measure time spawned astronomy, a science born of shadows and signs. Moonlight sheds an eerie glow on the ocean. The first observers had no notion of the moon's pull on tides, but the moon, like the sun and the stars, was a guiding light. From more than 30,000 years ago, timekeeping by the moon, a calendar carved on reindeer bone. Day by day, it records the lunar phases. But more important to our ancestors were seasonal alignments, moments when the moon or the sun marked a turning point. This burial site in Ireland is a Stone Age marker of the winter solstice. It was built so that on this shortest day of the year, the sun lights up the chamber of the tomb inside. Clouds permitting, it's never failed for 5,000 years. On December 21st, sunlight shines directly through a slit at this entrance. It happens only on this day. Lots of old buildings have celestial orientations. Many cathedrals are built east to west, but it's for heavenly reasons of another kind, Christian tradition. Further back in time, the pyramid builders of Egypt set their sights on the alignments of the stars. Weathering belies its former glory. Once a lavish mausoleum of limestone with a cap of gold, this is the great pyramid of the pharaoh Khufu. Inside, shafts supposedly align with special stars, looking out toward Khufu's route to immortality. An old Chinese map of the cosmos, but it was more. It was a reflection of the Chinese Empire. As the northern sky circles the pole star, so Beijing was built in rings around the imperial palace. This mix of myth and astronomy is epitomized at Abu Simbel. The temple was built by Ramesses the Great. No one's sure why, but it was so constructed that twice a year the sun lights up the gods within. It happens for a few days in February and October. Whatever the significance, we can only marvel at the precision. Whether for farming, fancy, or faith, the ancients knew their skies. Thousands of years ago, in the Celtic mists of northwest Europe, there were no temples to celestial gods. Instead, standing stones. Heroic rocks hauled upright by heroic men, rough-hewn markers to plot the progress through the seasons of the moon and the sun. Karnak, France, a megalithic wonderland, east to west, mile after mile of standing stones. Their precise purpose is lost. It had perhaps to do with the rising and setting of the moon and the sun. They're related to the great circles of Stonehenge in England, the most famous megalithic observatory. The key alignment is here, from the center of the circles, above the heel stone beyond, to the midsummer sunrise. The summer solstice, from the heart of an astronomical computer, 5,000 years old. It's so complex, a few archaeologists have suggested Stonehenge could predict eclipses of the sun. Unlikely, But eclipses of the moon are another story. Some of the oldest stones have intriguing alignments. These two mark the setting point of the midsummer sun. They also mark the setting point of the midwinter full moon. The moon passes through a cone of shadow cast by our planet. It's the time of a lunar eclipse. As the Earth blots out light from the sun, our shadow turns the moon blood red. The color is caused by our atmosphere. It bends the sunlight, and dust in the atmosphere deepens the redness of the shadow. In this partial eclipse, our shadow shows the curve of the Earth. Eclipses are simple, but why does the moon keep changing shape? Why does it go through phases? As it grows from a crescent to a full moon, the shadow isn't Earth's, but the moon's.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
As the moon wanes, the proportion of light to shadow that we see depends on the moon's angle to the sun. The ancients didn't understand it, but we can see how it works from out in space. From above the poles, we see the moon and Earth catching sunlight from the right. As it orbits Earth, the moon waxes and wanes to an observer on Earth. The cycle takes about 28 days. Here it is again, with the central frame showing the moon phase we see on Earth. The reason we always see the same face of the moon and never the other side is because the moon rotates just once in an orbit. If we could stop its orbit, we'd see it rotate. Observers of old may not have understood that it orbits the Earth, but they paid more attention than we do to the cycles of the moon. Eclipses of the sun are another matter. Some ancients understood that the moon was passing in front of the sun, but not that the Earth was a sphere. Here, the shadow of an eclipse moves across the planet. Within the black dot, the eclipse is total. On Earth, the sky is transformed. Little by little, the moon edges across the sun. A total eclipse. And with an exposure change on the camera, a halo appears. It's the corona, the outer atmosphere of the sun. Totality, as astronomers call it, can last over 7 minutes, a time. It's not just the moon that gets between us and the sun. A couple of planets do, Mercury and Venus. The Maya Indians of Central America knew all about Venus. Some of their temples were aligned to that planet. They used the complex motions of Venus to fine-tune their calendar. They could do it because Venus moves through the heavens in an 8-year cycle. The point where Venus sets today will repeat precisely in 8 years' time. The Mayans also used the stars of the Pleiades, the Seven Sisters. The Pleiades foretold the destruction of civilization once every 400 years. Tragically for the Mayans, the prediction was right. 400 years ago, their own civilization was wiped out by a race of men just an ocean away. The ancient Egyptians had different ideas. Sunset was the time to pay homage to a celestial wonder woman. She was Nut, a star-spangled goddess who swallowed the sun. By dawn, she'd eat the stars, too. But all was not lost. Nut would give birth to a new morning sun, and by sundown, to a new set of stars. Not all their notions were so fanciful. Egyptians were keen-eyed astronomers, and they noticed that the stars rise and set at a slightly earlier time each night. They saw the stars as patterns, as figures in the sky, and they realized that if the sun could be seen against those figures, it would move right across the heavens over the course of a year. This progress is what we call the ecliptic. The Babylonians gave it order. They split the ecliptic into 12 divisions, the signs of the zodiac. They imagined the sun tracking across the background stars. What they'd unknowingly observed was the Earth's orbit of the sun, our yearly cycle.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
The Babylonians believed their gods lived in wild places. To tempt them closer, they built ziggurats, but they were also observatories. We owe much to ancient Babylon. By naked eye, the Babylonians could record the movements of wandering stars, the planets. They knew 5 planets, with the sun and the moon, the 7 dominant objects of the sky. The Babylonians bequeathed them to us as the days of the week, their names recorded on the tablets of the cuneiform texts. The day of Mars. In French, it's still known as Mardi, although in English it's become Tuesday. The day of Mercury. In French, Mercredi, Wednesday. Jupiter Day. In French, Jeudi, Thursday. Venus Day. In French, Vendredi. For us, she's Friday. Saturn Day. Simply Saturday. The day of the sun, Sunday. And the day of the moon, Monday. The Greeks tried to apply science to the universe. With Earth at the center, they set the heavenly bodies in concentric spheres of crystal. The Egyptians kept faith with myth and a star that preceded the yearly flood of the Nile. One season, their calendars were badly out of kilter. They'd lost track of the days and the time when their crops would be irrigated. They needn't have worried. The dog star Sirius rose to the occasion, and so did the Nile. In northern lands, the cycle of the seasons was marked by standing stones and by observing the horizon. The point where the sun rises shifts every day. But twice a year, it stands still. These times were recognized as midsummer and midwinter. When it moves again, the season begins to change. The world over, the movement of the sun was a calendar. In this Native American cave, when an arrow of sunlight strikes this spot on the wall, it's midwinter. Chichen Itza in Mexico, a Mayan city steeped in astronomy and religion. A citadel and observatory. A place of sacrifice. Here, offerings were made to the gods to ensure the rains returned. A special monument, the Castillo, and, at the equinoxes, the shadow of a god in the shape of a rattlesnake, a serpent of sunlight on a stairway from heaven. They didn't know it, but ancient observers were recording how Earth's orbit of the sun causes the seasons. That orbit is called a year. Each day, due to the tilt of Earth's axis, the angle at which sunlight strikes us changes slightly. Over a season, it changes a lot. In the 6 months from winter to summer, the change is greatest of all. From this position, it's summer in the northern hemisphere. The north has short nights and long days. At the equator, it hardly changes. The south has long nights and short days. From this opposing position, it's winter in the northern hemisphere. Short days and long nights in the north, the long days and short nights of summer in the south. Our ancestors had a clearer view of the cosmos than we do. From city and suburb, the stars are fogged by lights and pollution. Nowadays, vistas like this are glimpsed only in the remotest places. In days of old, everyone saw the sky and knew the sky. They wouldn't miss the lights of the aurora, or a new star, a nova, the sign of birth. Or a comet, a heavenly courier. Some astronomers suggest it was a comet that led the wise men to Bethlehem. Would they even see a comet today? Shooting stars were once a nightly show. To the Egyptians, there were messages from the gods. When a meteorite fell out of the sky, they set it on a plinth and called it the Stone of Heaven. The ancients watched the heavens the way we watch soap operas. The sky was a panoramic screen full of characters and beasts, a way to make sense of the stars. They helped shape the legends of mythology we know to this day.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
Our star maps have changed, but myth persists. The names of antiquity are the constellations of modern astronomy. But how did they reach us? For they had origins in different places, in different cultures. Somehow, somewhere, the names of the constellations were codified. There's a theory it was the work of a lost civilization, a people dispersed more than 3,000 years ago after a volcanic disaster. They lived in the Aegean, on an island in the eastern Mediterranean known today as Thera, or Santorini. They were traders and navigators. Archaeologists have unearthed a wealth of artifacts and a seaport dating from 1450 BC. And there's evidence, some astronomers say, that star maps were made here, charts that name the constellations as we know them today. Perhaps those ancient observers on Santorini fed the legend of Atlantis, learned astronomers in flight from catastrophe. How high the moon, how far the stars. Around the world, astronomers pursue an age-old quest. They're down-to-earth people, scientists who understand the insignificance of our planet in the grand scheme of things. Since the time of the ancient Egyptians, the skies have scarcely changed. And the questions are the same. Will we ever reach those stars? How vast are the heavens? Questions that take us to the edge of time. In the quest to put a yardstick across the universe, the moon is our first measure. The moon is our only natural satellite. It's 250,000 miles away, and its light takes only a second to reach us. The Earth is one of 9 planets that orbit the Sun. The Sun is 93 million miles away, and its light takes over 8 minutes to reach us. From the outer planets, the Sun is just a brilliant star. Neptune is 3 billion miles from its warmth. Sunlight takes 4.5 hours to arrive here. Beyond the planets are the stars, but to the naked eye, they look the same, two-dimensional. Now, thanks to astronomy, we know much of their nature and their distance. Among these stars, if you don't count the Sun, is our nearest star, Alpha Centauri. It's the big one to the left. Alpha Centauri is 25 trillion miles from Earth. Alpha Centauri is more than one star. Indeed, it's more than 2. It's a triplet. Their light takes almost 4 1/3 years to reach us. Or, as astronomers would put it, Alpha Centauri is 4.3 light years from Earth. Out here, at such a distance, the Sun is a dot, a modest star visible to the naked eye. Onward and outward, and some 200 light years from home, the stars of W Ursa Majoris, twins that exchange material. farther and through the stars of Orion. From Earth, they're a two-dimensional pattern. Out here, we realize they lie at different distances. They have depth. We've reached 1,500 light-years and the heart of the constellation, the Orion Nebula. It's a great cloud of dust and hydrogen, a cocoon of gestation, a place where stars are born. If we kept traveling onward at the speed of light, it would take another 30,000 years to reach the center of our galaxy. Instead, we leave it. We journey to a vantage point outside, where we look back at our galaxy, a spiral of 200 billion stars, the Milky Way. But it's just one in a local group of galaxies. That group, in turn, is part of a bigger group, a supercluster. Superclusters form webs, networks that cross the universe, the voids between seemingly empty of galaxies. But there's more to the cosmos than meets the eye. Over 90% of its mass is invisible. It's called dark matter, a sea of exotic particles that possibly fills the universe.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
The Milky Way is big. A beam traveling at the speed of light at 186,000 miles a second takes 100,000 years to cross our galaxy. At the same speed, a journey through our solar system is a matter of hours. How do astronomers know all this? How did they learn to measure the universe? The story begins over 2,000 years ago in Egypt. It involves basic geometry, calculations familiar to temple builders. It gave the world the first unit of astronomical measurement, a unit as big as the world. The reflection of the sun shining directly down a well in Aswan. 500 miles to the north, in Alexandria, a column cast a shadow. It was noon in both places, so why the difference? According to legend, a librarian called Eratosthenes realized it was due to the curvature of the Earth. When the sun was directly overhead in Aswan, it was at an angle in Alexandria. That caused the shadow. The difference in angle was a 50th of a circle, so the distance between Aswan and Alexandria must also be a 50th of something, a 50th of the circumference of the Earth. That's geometry. And that was Eratosthenes' reasoning. He was right. The Earth's circumference is about 25,000 miles. 200 BC, and it was known that Earth was an orb in space. Where it lay in space was tougher. A Greek idea put the Earth at the center of things. Around it, set in a series of crystal spheres, orbited the moon, the sun, the planets, and the stars. But the planets were a puzzle. They were called wandering stars. Their progress through the heavens could be erratic. Some would stop, reverse, and proceed again. The Greek astronomer Ptolemy had an answer. He accounted for their wanderings with epicycles, little orbits made by the planets around their main orbital paths. It's a clumsy idea, but it seemed to fit the observations. It seems to work for planets like Venus and Mercury, which speed across the sky at twilight. But it fails with others, like Mars. For 1,400 years, there was no progress. Then, an eagle-eyed Dane named Tycho Brahe had half a good idea. He still had the sun going around the Earth, but he had the planets going around the sun. The passage of a comet sparked his theory. Observing the great comet of 1577, Brahe calculated that in one night, its movement against the background stars was much less than the moon's. This put comets among the planets, smashing the notion of crystal spheres. But Brahe still had Earth at the center of the universe. The Polish astronomer and cleric Nicholas Copernicus had already knocked down that one. He put Earth in its place as a planet orbiting the sun. But he assumed that the orbits of the planets were circles, and he couldn't explain the eccentric loops of Mars. A German mathematician, Johann Kepler, could. He worked out that the orbits of the planets aren't circles, but ellipses, and that the speed of the planets depends on their distance from the sun. The picture of the solar system was complete. Enter the English scientist Isaac Newton. Newton explained more about orbits with his famous theory of gravity. He imagined a cannonball fired from a mountaintop. Fire it faster, and it goes farther. Fire it fast enough, and it goes into orbit. It becomes a satellite, like the moon around the Earth. Or the many moons that orbit Jupiter. Newton's genius was to recognize that the force that makes a cannonball fall to Earth is the same force that governs the motions of moons and planets. It's the force that dictates the speed of orbits. In the solar system, the closer a planet is to the sun, the faster it must move to stay in orbit. And it's the force that boosts spacecraft as they explore the planets.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
At the dawn of modern astronomy, there was a map of the solar system, but it was a map without a scale. The dot is Venus crossing the face of the sun. It happens when the orbit of Venus carries it through our view of the sun. Seen from two different places on Earth, Venus makes two different tracks across the sun. That difference is the key to the planet's distance from Earth. Simple trigonometry gave astronomers the answer, and that answer provided a scale for the solar system. But how to measure the stars? As our planet circles the sun, we'd expect the nearer stars to move from side to side as our perspective of the cosmos changes. Astronomers looked in vain for the effect, but a Dane called Ole Romer found another effect of the Earth's orbit of the Sun. He was observing eclipses of Jupiter's moons. They came sooner than expected, he discovered, when the Earth and Jupiter were on the same side of the Sun in their orbital paths. The eclipses came late when Earth and Jupiter were on opposite sides and farthest apart. The reason was the time taken by light to travel from Jupiter to Earth. Thus, Romer showed that the speed of light was measurable, not infinite. But the puzzle remained. How could the distance to the stars be measured? As telescopes became larger, more and more stars sprang into view. In the 18th century, with the huge telescope he built, English astronomer William Herschel began to map the heavens. Painstakingly, he counted the stars. There were thousands. He produced a chart of how he thought they were arranged and put the sun near the center. Herschel thought this was all there was of the universe. Evidence that there was more came from Birr Castle in Ireland, where the 3rd Earl of Rosse built an even bigger telescope. It was the mid-19th century, and Rosse had discerned faint, wispy clouds. He drew them. Within some clouds were swirling structures. Beyond the Milky Way, Rosse had glimpsed mysteries. Astronomers were finally coming to grips with the distance of stars. New, precise observations revealed that stars do shift position as the Earth orbits the Sun. It's hard to see because they're so far away. The effect is called parallax. It's measured by observing a star from one side of our solar orbit, then 6 months later from the other. How far the star shifts depends on its distance. The closer the star, the more it shifts. Astronomers found that stars are incredibly distant, light years away.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
From the depths of the cosmos, a star that beats like a heart. It's called a Cepheid. Astronomers can tell its distance from the rate of its pulse. Cepheids are celestial beacons that help measure some of the most distant objects in the sky. Cepheids beat in globular clusters, collections of stars that hover outside the main disk of our galaxy. By measuring the pulse of a Cepheid within, the distance of the cluster can be worked out. Globular clusters are too remote to measure by the parallax method. The observation of Cepheids has helped map the structure of the galaxy. The Sun isn't at the center, but 2/3 of the way to the edge. At last, the Sun was dethroned from its place at the hub of the universe. But there was another surprise. Observers have seen it since ancient times. It's a fuzzy patch in the constellation of Andromeda. Near or far, no one could tell. Then, in 1923, the American astronomer Edwin Hubble discovered Cepheids in its outer reaches, so faint they were far beyond the stars of our own galaxy. Hubble was looking at another galaxy, more than 2 million light-years away. As Hubble peered deeper into space, he found more and more galaxies of every shape and size. Hubble unveiled an expanding universe. Galaxies traveled outward in all directions. The farther away they were, the faster they appeared to recede. The evidence was in their light. It shifted toward the red end of the spectrum, a sign of lengthening wavelengths. The wavelengths were stretching because the space between the galaxies was stretching. The galaxies were relentlessly moving apart. Edwin Hubble had stumbled on a clue to the origin of the universe, the Big Bang. His brilliant observations revealed an ever-expanding universe, a universe that must have a starting point, a moment when time and space began. Today, in Towers of Astronomy, the quest to measure the universe goes on, but our instruments are crude. Observations by the world's most powerful optical telescopes have a 30% margin of error. We need finer devices. Like the satellite Hipparcos, clear of atmospheric distortion, it surveys the nearest stars, measuring distance as never before. Another is the Hubble Space Telescope, continuing the work of Edwin Hubble himself. In 1994, it studied Cepheids in a galaxy too distant for telescopes on Earth. Its observations put astronomy in a spin. The Cepheid set the distance of the galaxy at 50 million light-years. That distance, when linked with the galaxy's redshift, told astronomers that the universe was only 9 or 10 billion years old. If the universe is so young, how is it that stars much older have been measured? Are the winking Cepheids sending false signals? These Cepheid readings are probably right. It might take years to see them in context. Our picture of the Big Bang could well be all wrong. Indeed, was there even a Big Bang? And if there wasn't, why does the universe expand? These are the questions scientists confront as they tiptoe toward the edge of time. In years to come, our ideas of the cosmos may be as quaint as those of ancient observers.